Powerus. Powerus. I may not know how to pronounce that name fully, but I do know what's going on inside of here. Now, there's not a whole great deal of videos or information on the web about this brand of amplifier to this day, but they've been around for a couple of years now, and they're starting to pop up more and more in different countries, and I thought that it would be a great opportunity now to grab a couple of examples of these amplifiers and talk you through in detail each section of the circuit, how it's been assembled, and that should give you a good idea as to whether this brand of amplifier is worthy of your next purchase. But there's one thing we need to get out of the way first. Yes, this amplifier is made in Brazil. However, we need to stop putting all of the amplifiers made in Brazil by different manufacturers under the same umbrella in terms of how they perform, how they sound, and their reliability. Just because they're made in the same country does not mean that they share exclusive design features with each other, and it doesn't mean that they will act the same or have the same reliability or pretty much share any similarities at all, other than the fact that they're made in Brazil. The same goes for all kinds of other brands of amplifiers like JL Audio, JBL, Rockford Fosgate, all kinds of different amplifier brands will be made in the same country, but they were designed by different people and they will be built with different levels of quality, etc. Just because they're made in the same country doesn't mean that they're gonna share the same characteristics when you use them. So I just wanted to get that out of your head first. Just because this is an amplifier made in Brazil does not mean that it shares any similarities with any other amplifiers also made in Brazil. And also, people need to stop putting full bridge amplifiers under the same category as one style of amplifier either. Full bridge has been around probably longer than you have, and it's seen in the likes of JL Audio, Rockford Fosgate, JBL, Alpine, Orion HCCA amplifiers have all made full bridge amplifiers in the past, and whether an amplifier is full bridge or half bridge does not mean anything to do with how the amplifier performs, its reliability, how it sounds, etc. It's just a design topology as to whether the amplifier has the sine wave coming out of the positive terminal only, with negative being ground, allowing you to take two amplifiers and strap them together, or whether the amplifier has sine waves coming out of both positive and negative terminals out of phase from each other, a bit like having two amps already strapped in the same PCB. That's all full bridge means. It doesn't mean anything else. It doesn't mean that the amplifiers can't do this, can't do that, sound like this, sound like that. What you're experiencing there is just similarities in specific Brazilian brands that have kind of gone down a specific certain design route. And if those Brazilian brands made half bridge amplifiers instead, they would still be the same kind of sounding, kind of reliability as their full bridge counterparts that they actually make. So when you hear that a specific amplifier is full bridge, don't put it under the same category in your head as other brands of amplifiers that just happen to be full bridge and maybe happen to be made in Brazil at the moment. Just think that, okay, this is full bridge, that means there's a sine wave on positive and negative terminal and I can't strap it. That's all it means. Let's start by taking a look at the heatsink design. So it's a nice black, it looks quite understated. We don't have any peak figures written on it. It just says 8,000 watts RMS class D, which is the truth. The heatsink does have some decent weight to it, which means that there will be some nice thermal mass for all of the MOSFETs to dissipate their heat throughout. There are some ribs on the front, although they're quite shallow, but it will help a little bit with increased surface area for dissipating heat. On the top of the amp, we have our status LEDs. We have the limiter, which I'll get onto later. We have the on and protect, which is a bicolor LED, which is great. Clip LED, and then this LED, which it was like a protection mode, but it will tell you specifically if your amplifier has been subjected to voltages less than 7 volts, damn, that's pretty low, or greater than 16 volts, which is great because most amplifiers have the protection LED integrated with all modes of protection, whether it's short circuit protection, under voltage, over voltage, it's all just the same LED. So when your amplifier goes into protect, you've no idea what protection mode it actually has triggered without kind of doing some kind of diagnostics. Whereas with this amplifier, it'll tell you specifically if your voltage is dropping too low due to your ground point is kind of wobbled loose, or your fuse holder is melting, or you've got some crazy voltage drop going on. It'll instantly tell you. Red LED will show you that you drop below 7 volts for a period period of time, which is obviously something you need to look into. And it'll also tell you maybe your alternator is starting to malfunction and it's sending greater than 16 volts to the amplifier. You also know that that is what caused the amplifier to go into protection as well. Having the clip LED here is fantastic because it means you can set this amplifier up without needing stuff like DD1 or oscilloscope, because the clip LED will be dead accurate because it is based on a comparator that listens to the output sine wave and compares it to the rail voltage inside the amplifier, which is what causes clip. So the clip LED will be dead accurate. Use that to set your amplifier up, and you don't need any other tools. The only thing I would quite like to see would be some kind of remote wire or something that allowed you to bring a clip LED up to the front of the vehicle so you can monitor it at all times, because obviously you're not going to be looking over your shoulder at the amplifier all the time seeing if it's clipping or not, but you can use that to set up the amplifier initially to clip point, and it's really easy because it's all built into the amp. On the sides of the amplifier, there are quite a lot of vents. There's quite a lot of kind of open venting here. You must be careful not to get any wire strands from your power wires or your speaker wires into any of these vents. I actually see this so common. Whenever I open an amplifier to repair it, I would say like 6 or 7 times out of 10, the amplifier has copper wire strands just floating around inside of it, and they obviously find their way onto high voltage parts and short out parts of the circuit, and that has been the cause of failure in a number of repairs that I have done. So just bear in mind that there are quite a decent amount of open vents here, so take care when you're stripping cables and putting cables into this amplifier. You don't let any wire strands get inside. Power terminals, then you should be able to fit a 70mm true American gauge wire into these guys. Obviously this is an 8000 watt RMS amplifier. It would be nice to see dual terminals, but I imagine that may cause the amplifier to be bigger than it is at the moment because the space on the PCB. To be honest, if you're running this kind of amplifier anyway, it's a good idea to have dual inputs. If you're running it to extremely high output with relatively low impedances, if your impedance rise isn't that high, and if you're doing long demos and stuff, it would be great to run dual inputs on this. I'd highly recommend that. Over on the other side, we have the speaker terminals, which are quite small. It would be nice if these were a little bigger, if you wanted to run multiple cables into the terminals for going off to all your subs, or maybe like how the Korean amplifiers do, give you a set of 4 terminals that are just internally wire splitted, to give you more holes to shove your wires in. With this kind of output, you would, if you're running multiple subs, you're splitting it off into loads of different subs, you would need to have some kind of splitter box or some kind of distribution box for all of your wires, to then just have a single pair of wires going into here. So it'd be nice to have a bit more option there for putting in more or thicker cables in there. The RCA inputs, unlike some other Brazilian brands, we do have 2 RCA inputs that are both in, rather than one being in and one being out like we see on some of the other Brazilian brands. You don't need 2 RCA inputs. It's a mono amplifier, but for some reason head units have grown up to give you left and right subwoofer output, so obviously you're bringing both RCAs to the back of the car anyway. Having only one RCA input means you either have to leave one dangling, or you have to go a Y splitter from 2 into 1, which is just messy. So nice that they've put 2 inputs in the RCAs here. Okay, that's about everything on the outside. Let's flip her over and have a look first at the cooling method on this amplifier, because it is actively cooled. We have these 2 fans which are sucking air in from the outside and blowing cool air over these fins in the heatsink towards the output section, and then we just have a natural exhaust out through these vents. That's pretty cool because the air will pick up quite a lot of thermal energy from the decent surface area from all these fins. We are not blowing air directly over the MOSFET legs like in the tire amps, so any dust or dirt that comes in through the fan isn't likely to get lodged and caught up on the MOSFET legs like it does on the tire amps, which is an issue because that can be conductive and end up shorting out the FET. So that's pretty nice to see. This will generate a positive air pressure inside the amplifier because we have active cooling coming in and then passive exhaust coming out. So there'll be a slightly positive air pressure in here, which there's various arguments as to what's better, positive or negative pressure with cooling, but I think I prefer positive because it means there's more air pressure and air particles in the amplifier to take up and soak up the heat and then get it out of the amplifier. So that's cool. Let's dive in and have a look at the power supply circuit design. This is an interesting Brazilian because unlike all of the other Brazilian amplifiers, This is not running with a PIC chip to control the power supply, switching frequency, dead time, and protection circuit. This is more like an old school Korean or Japanese built amplifier from a very reputable brand. This is using the SG3525AP to generate pulses for the power supply MOSFETs to run on. And this is a really good diverse chip that you can do a lot with in terms of regulation of the power supply circuit to control the rail voltage and pretty snappy quick protection circuit. So because there is no PIC chip, there is no health check mode at the start when you power the amplifier up. However, from what I have seen, these amplifiers do have an extremely quick, effective protection circuit, so that if you do have a blown output MOSFET, when you try and power the amplifier up, it doesn't smoke up the whole freaking power supply like it does in the god ancient old Korean amplifiers. Absolute nightmare things. So PWM generation is here, and then the drivers for the power supply MOSFETs are here. Some beefy ass bipolar transistors, and these will be driving the MOSFET gates directly through 10 ohm gate resistors. So there's no ESD control, EESI control here, just absolute raw hard switching power, unlike the likes of the amplifiers coming from Orion and B2 and some of the Sundown amplifiers, which have the power supply massively bottlenecked by regulations, which cause them to use like 260 ohm gate resistors in the power supply to soft switch the power supply, which does kind of limit its power capabilities slightly. None of that going on here. You've got absolute maximum switching potential from the power supply section here. Nice low ohm gate resistors, driven by some pretty beefy transistors over here. This will work great. These will have loads of headroom in terms of how much current they are supplying to the MOSFETs. They're not going to draw barely anywhere near the current limits of these transistors, and because they're surface mount, they're soldered to the thick PCB, so they're going to be able to dissipate their heat really effectively. So that's going to be incredibly reliable power supply drive circuit. The power supply MOSFETs which are being used are really decent IRF 1404s. I first saw these in the Taramps HD line. These are actually very good MOSFETs. Taramps didn't implement them very well with the drive circuit and just the general power supply design, but for these MOSFETs, the performance versus the price is a sweet spot. They could have gone with higher power supply MOSFETs, but the price of the amplifiers would have gone up considerably without really any great improvement in performance or cooling or anything. These are nice low RDS MOSFETs. They have a relatively decent low input capacitance. They are really good MOSFETs, and there is a whole bunch of them here, and they're driven really strongly. With the power supply transformers, rather than having just one large transformer as seen in the Taramps HD line and the Band of Viking line, we have much smaller transformers all parallel together, which actually this has been proven to be a better design than just having one large single transformer, which can have all kinds of issues of its own. Having multiple smaller transformers that then parallel the rectifiers is a better solution, and this should be really powerful and really reliable. On each transformer, we have two MOSFETs in parallel on the push side and two MOSFETs in parallel on the pull side. So each transformer is being pushed and pulled by a pair of MOSFETs on each side. So yeah, you'll have 2, 4, 6, 8, 10, 12 MOSFETs per side, 24 in total for the 6 transformers. Okay, output section time. As with pretty much all the Brazilians, you don't get a great deal of rail capacitors, which will mean that this amplifier does less dynamic power compared to your average kind of Korean half bridge that has a whole bunch, the whole board is filled with rail caps. So you'll generally see Brazilians do roughly the same dynamic power to their certified power on the dyno, whereas the Koreans, the dynamic power can all be like 2 or 3 kilowatts higher than the certified power, because in the pulse, the rail voltage doesn't droop instantaneously like it does in these amplifiers with less rail caps. So, but that's fine. We'll still get the rated power out of the amplifier. Just means that there's less power available dynamically before it starts sagging the rails down and drawing majority of the power from the power supply section. So it would be cool to see a Brazilian amplifier that is built as well as this is so far, that does have really crazy number of rail caps to kind of give it that Korean dynamic power punch and sound, but it would mean the amplifier was bigger, more heatsink, more cost and everything. So I guess with the affordability of these, you can just buy a bigger bigger amplifier than you need, turn it down a bit, and then have the dynamic power there available because you've got a bigger amplifier in the first place. So you can just do that. PWM generation, converting the sine wave into pulses, is done over here. We've got a CD4047 and a bunch of op amps over here. Won't go into too much detail about how that works, but we're going to look at the switching frequency or the sample frequency in a little bit when we power this up. The output drivers, we have the same drive ICs that the Taramps HD line use, SI8214BB. I'm actually a great fan of this. The Taramps line of amplifiers are known for being unreliable, but that's in the power supply section. That's why everyone's like, oh, they always catch fire, because when the power supply section goes down, it's very smoky, and that's where you get all the flames and stuff from. The output sections in the Taramps amplifiers are actually really reliable. Like, I don't generally see a lot of Taramps HD series amplifiers or other series for that matter that have randomly dead output sections. It's usually the power supplies that go. So I am pleased to see this driver here. It's pretty decent, it's pretty reliable, and we also have it buffered by some drive transistors as well. So this chip isn't directly driving the MOSFETs, so the stress is taken off the chip, just in providing the drivers with the pulses for them then to drive the MOSFET gates directly. We have low value gate resistors, again 4.7 ohms, and we have a diode in parallel with the gate resistor so that when the MOSFET turns off, the excess current that is still on the gate can quickly go through the diode rather than having to go through the resistor to ground to turn the MOSFET off quickly. The output MOSFETs themselves are the same ones that you'll find in the Banda Viking 8K, IRFP 90N20D. These are absolute beast MOSFETs. These are fantastic, low RDS, extremely high pulse drain current MOSFETs, and they should work fantastically in generating huge amounts of power without generating a bunch of heat. And they're not too difficult to drive either, and they have pretty good switching characteristics. So we'll see when we power it up shortly how it handles with the switching frequency, what switching frequency they've chosen to use, and how the drive circuit has been designed with the dead time and everything to make sure that these are running optimally. And then on each side of the bridge, we have the output filter inductor and some filter capacitors as well there before the speaker terminals. We'll take a look at how noisy the wave is on the speaker terminals, you know, how much filtering is actually going on. But because this is generally going to be used as a subwoofer amplifier for the most part, I imagine, it shouldn't matter too much because a subwoofer voice coil is in itself an inductor anyway. So any sort of high frequency switching noise will get filtered out by the coil itself anyway. So we'll take a look at how well this performs in a bit anyway. Just other things to note, we have the auxiliary voltage section over here. We have the 7815 and 7915 regulators here. That will be taken from the auxiliary winds from these transformers. And we have the 7805. So these are just regular voltage, you know, regulators. Not the most efficient way of supplying a fixed voltage to these chips. Be better to use some kind of buck converter or something like that, much more efficient. But to be honest, they're not drawing a bunch of current, so it's not too bad. You know, amplifiers have used this style of voltage regulation for absolute decades now, and it works okay. They're pretty reliable, so it's fine. If we take a look at the preamp circuit, pretty similar to all of the other amplifiers from Brazil, really, to be honest. On the side, we have some knobs which will give you a level adjustment from 6 volts to 0.25 volts. So it will take a relatively high input voltage. Some of the issues with some of the other Brazilian amplifiers is that the RCA voltage can end up being too high, which is not ideal. But on this one, it looks like you've got a pretty decent headroom there for input voltage. Limiter, which we'll get onto in a little bit. I'll explain how that works later. Low pass filter, the minimum is 80 hertz. And the max doesn't give you a value. So, but 80 hertz is not low enough for me. For a subwoofer application, we're going to take a look at this in a little bit, but that needs to be much lower for these amplifiers to sound similar to how your Korean half bridges do. The amplifier stages itself in these Brazilian amplifiers compared to Koreans don't sound much different from one another, but this difference in sound comes from the preamp section, and it's mostly this. So if you run this low pass knob anything other than 0, even if you just turn it up by a small bit, basically that's now going to probably be like 120, 150 hertz on the low pass. So you're going to be sending way more higher kick bass frequencies than you ever would do with your Korean half bridge amplifiers, which is going to make this amplifier clip earlier. It's going to clip on the kick drums, and it's not going to sound anywhere near as smooth and refined and deep as your Korean amplifiers. So keep that on minimum if I were you, if you're using this with subwoofers, and also apply another low pass filter from your head unit or DSP that is set to around 50 50 or 60 hertz, just with quite a steep slope, just to get rid of any super high bass frequencies that your subwoofer is not going to like, because generally the kind of subs that we use over in Europe and the States and stuff for low frequencies don't like playing the frequencies up that high. Anyway, not much impedance rise up there, drawing a bunch of current from the amplifier, clip light flashing on the kick drum. That's not what you want, so keep that down low. High pass, the minimum is 5 hertz. We'll see how steep the slope is on that, see whether that's affecting any 20-25 hertz stuff. It shouldn't do. I would honestly keep this down at 5 hertz again. Even if you turn this up a little bit, you can see it goes up to 200 hertz. So if we go up to there, that could now be at like 35 hertz, which is going to be crap. It's going to be eating away all of your nice 30, 28 hertz bass notes. So I would keep that on minimum. And if you're going to have to run a high pass, do it actively. Do it on your DSP or on your head unit. And then we have this boost section, which I would honestly advise not touching unless you really have to kind of wean out some kind of weird dip in your response somewhere. But that's pretty rare, to be honest. And I hate that this is called gain. That sucks, because people are going to get confused, because usually you call this will be the gain, but over here you have a bass boost knob that's also called gain, so that's going to confuse some people that haven't been in the scene for a long time. But you can set the frequency that you're boosting between 28 and 400 hertz. So I guess that's better than just having a fixed 40 hertz boost, for example. But honestly, you don't need to use this. You shouldn't use any of this, and I wouldn't use any of the high pass or low pass stuff. Just do that actively. The limiter and the level is the only ones that you should really be touching when you're using this for a subwoofer application. The only time when this might be useful to you is if for some reason you're using this amplifier with your factory integrated head unit that has its own high pass filter or subsonic filter that rolls off the low frequencies, and you're using like a high to low level converter into this amplifier. So that would mean that all of the higher bass frequencies have a much higher amplitude than the lower stuff, in which case you could turn the level down and you could set it to boost like 28 or 30 hertz a little bit, just to bring those lower frequencies back in line with the higher frequencies that are being passed through without being touched, and bring back the lower stuff that is being attenuated by the high pass filter from the factory head unit. But to be honest, who the hell is going to be running an amp like this on a factory head unit with a line level converter? But these controls are all present on the smaller range of amplifiers from Powerus as well, so that might come in handy for the smaller amps and people using with the factory head unit still. So yes, generally don't touch it, but it can be useful in very certain circumstances if you don't have a DSP. Now, this is where it starts to get really good. Let's talk about the assembly quality of this thing. I want to know, how well is this thing going to hold up against vibrations that are typically throughout the whole vehicle in a system running an amplifier with this much power. Whether you mount this to the box or whether you have a dedicated amp rack, there is going to be a ton of vibrations throughout the whole vehicle, regardless of where you mount it. The transformers, these are absolutely solid. There is not a single wire strand that is loose. The cores and the whole thing is so solidly mounted. I don't get any wobble. I can't move that whatsoever. It feels like absolute concrete fixed to the PCB. And like I say, every single wire strand is encompassed in some adhesive. Not a single wire strand is loose. These are some of the best seated down transformers that I have seen in a long time. Far superior to anything I've seen coming out of Korea, and better than pretty much all the other Brazilian brands that I've seen. Banda are pretty good. The Taramps have that one great big transformer, which generally is so heavy it's quite well seated anyway. But damn, this is freaking awesome. Very well seated down transformers. You are not going to get any rubbed leads or any vibration damage issues from the power supply transformers in this amplifier. Moreover, when we start to look at the rest of the components on the board, the main rail capacitors, these are actually soldered, they're seated right down against the board. Some amplifiers I've seen they're slightly up and raised, which means that they wobble slightly. These ones are right down on the PCB. We have adhesive between each capacitor. I have no wobble or movement on these snap-in leads whatsoever, so these aren't going to be going anywhere anytime soon. All of these resistors here, these all have adhesive across the top and on each of the edges. These are solidly seated down to the board as well, no movement in these. All of the film capacitors are CAs down to the board. They're not going anywhere. The The smaller capacitors here also have CA on them. The output inductors, which are an issue in the Sound Digital and Triumph's amplifiers for vibration damage, they snap all the freaking time because they are super loose. These, rock solid, not going anywhere, absolutely rock solidly secured to the PCB. This is pretty insane. This is a fantastically assembled amplifier. I can't see any real weakness anywhere when it comes to potential vibration damage. This is fantastic. One of the best assembled amplifiers I have seen in a long time. Far superior to anything coming out of Korea or China, and pretty much better than all the other Brazilians that I've seen so far. The last thing I want to check is how much the board flexes from the middle, which may put stress on the MOSFET legs across the side. The Stetson suffers horrendously from this. The Stetsons just snap all of the freaking MOSFET legs because the board is flexing so much from the middle, it just wobbles and metal fatigues the legs across the side. So let's have a look. There's a little flex there, but that resonant frequency of the board here, very high frequency. I can't see that really being an issue unless you're playing, you know, sort of 200 hertz and this is mounted to a box that's flexing at 200 hertz. So that's going to be okay. It would be nice if this amplifier did have maybe even just one support screw here to the center of the PCB. Would absolutely drastically change that and would bring that up to the level that the rest of the board is built to, because I'm getting a little bit of flex on the center of the PCB here. I can't see that causing any issues though, because it is so tight. It's a very tight PCB and it's very thick as well, so that frequency is very high and it's pretty stiff. But it would be nice to have even just one support screw in the middle here where the flex is, you know, at its highest point. But overall build quality of this thing, I am freaking blown away. This is superb, down to every last component. Even these inductors, which we'll get onto in a minute, not all amplifiers have these. These, again, are completely doused in adhesive. They're one whole solid piece, not going anywhere, no movement whatsoever. If we take a look at the back of the PCB here, this is top class, I'm not gonna lie, compared to some of the absolute nonsense that we see coming out of Korea, China, other Brazilian factories. This is some freaking clean as soldering. No flux residue left behind whatsoever. No like huge stray like solder strands. We've got massive thick bars there. Huge thick bars for the high current power supply section. This is absolutely stunning. Really beautiful looking rear of PCB, and it's not often that the back of the PCB looks like this. Usually it's just covered in flux and they don't really care about it and it's just kind of a mess. But this is really awesome. Super thick jumper bars again on the back of the PCB, and the PCB itself isn't even that thin. It's a really decent thick PCB with high current trace thickness as well. There are some additional kind of fusible leads here as well, what we mentioned earlier. On the top of the PCB, there's some cleverly thought out trace work that will go fusible if there is any failure. Well, it looks like we've got some other implementation of that on the back of the PCB here to prevent catastrophic failure of other parts of the amplifier if there was a problem. But man, honestly, I can't get over this. This is one of the nicest back of circuit boards that I've seen in a long time. Unlike some other Brazilian brands, none of the component markings have been sandblasted or scratched away. You can see every single component model that is being used here on the board with nothing hidden, masked away, or left secret. Absolutely fantastic. Means that if you did want to give this a go repairing yourself, or you're comparing it to other amplifiers, you can see exactly what is being used in this amplifier that makes it tick. Not only are the component markings left intact, but on the PCB, we actually have written there by each component what it should be, not just by the ICs, by all the transistors and all the resistors and capacitors. So if this board was completely stripped of components, you could, without too much knowledge, completely rebuild this from the ground up just by looking at the component markings on the board for what parts should go there. There are also some markings that explain what some of the trim potentiometers do. For example, here, this one is to adjust the DC offset on the speaker terminals, and this one here would be to adjust the limiter sensitivity. So this makes this amplifier incredibly easy to service. Even if you have not been given a schematic, just by looking at the board here, there are some things that are self-explanatory and that really help when you're trying to work out exactly how this circuit works, or maybe how to perform a repair. Now, if you were to be attempting a repair on an amplifier like this, it is quite dangerous because there is significant high voltage, pretty high current available in the output section when this amplifier is powered up normally. However, as you may have seen in some of my recent videos where we have been injecting our own low voltage rails into the amplifier for safe diagnosing and checking the output section is working okay without crazy high voltages there ready to blow our new components or to cause any extra damage, we've been injecting our own low rail voltages into the amplifier. And in order to do that, we've had to make some modifications, remove some components, etc. to do that. However, completely unknown to me until this point, Powerus have already implemented some of the things on the PCB to allow us to do that. It seems like they already had this in mind when it comes to repair. So firstly, let's take a look at just by the rectifiers here. You can see here there's a little cut in the trace, or a little gap in the trace here between here and here, and there are some solder bridges across them. So what this is the trace which is coming from the secondary wires of the transformers into the rectifiers. So let's say you were repairing this amplifier and you wanted to power the amplifier up without the big 200 volt rails coming into the capacitors and sitting on the output section, just so you could check some of the PWM generation circuit or the protection or the drive circuit without the high voltage being there. All you'd have to do is just remove the solder from these bridges here and here, and that would prevent the 200 volts rails being generated and coming into the output section. But it would still allow, because the power supply section will still be switching, it would still allow the auxiliary voltages plus minus 15 and plus 12 on the negative rail to make their way to the voltage regulation circuit so that the drive circuit becomes active. So you can inject your own low voltage rail into this amplifier by simply removing the solder bridges here and here, and then conveniently putting some test probes into these points here, which are actually for the main rail. And yeah, you can power this amplifier up with as little as 10, 20, 30 volts worth of rail instead of 200 volts, which makes working on this not only way safer, but also much better, because if there is anything you've missed or haven't repaired properly, or if there's any damaged components still when you try and power this up, by having a low voltage rail will mean that you aren't going to be killing all of your new expensive MOSFETs you may have just fitted, and it's going to be much easier to diagnose and repair as a result of that. It's possible to do this with any amplifier, as I've been showing in my recent videos, but these guys have designed the PCB in such a way to make it super easy to do that and to perform a safe and serviceable repair. The designers have also implemented some measures to prevent catastrophic failure, like butterfly effect failure, if anything was to go wrong with this amplifier. So some amplifiers from back in the day may have actually had various fuses around different parts of the board that will blow to prevent excessive current from draining into a shorted component, for example. On this board, we kind of have the same thing, but instead of fuses, there are parts of the PCB trace which are deliberately bottlenecking the current. So, for example, if this MOSFET here was to short and the power supply section was not to shut down immediately, then instead of this MOSFET cooking up, catching fire and burning the PCB, or potentially killing other parts on the circuit, I imagine that this trace will be designed to blow open, to fuse, to isolate this shorted MOSFET from the high voltage, high current rail voltage in there. And then with that trace blown, when it comes to repair, there is a exposed pad there ready to be soldered onto to jump over the blown trace to bring this amplifier back into fully working operation. There are more examples of these fusible traces on the board elsewhere, like just here. You can see this tiny little thin trace in between these exposed pads, and this area of the board, I imagine this is for the 12 volts regulated voltage that is applied to the drive ICs here for the low side. That could be for that, but we'll find out when we power it up. But yeah, I really like these little implementations so that if this amplifier was to fail, it prevents catastrophic, damage being caused by just continuous current being dumped into a shorted component, so that the weakest link in the chain here is going to be these fusible traces, which will have been designed to work absolutely fine under normal operating conditions, but blow open if a fault was to occur to prevent further damage elsewhere on the board. Now, you may have noticed that there are some locations here for output MOSFETs that are not filled on the board. You may be wondering, well, why are there spaces for additional MOSFETs that aren't actually present? Well, these Powerus amplifiers are all available in varying ohm load options. So you can buy this 1 ohm 8K amplifier in also a 0.5 ohm, 2 ohm, and 4 ohm version, so that you can really marry this up with your system, your subs, whatever it is you need. And obviously with the different variants of this amplifier will demand different models of output MOSFETs, rail capacitors, and transformers. And in this 1 ohm version, the lower with impedance you go, the higher the current, but the lower the voltage. So we end up with really, really high current, but lower voltage output MOSFETs. But for example, with the 4 ohm version, there's going to be some crazy high voltages going on in here. And when you have voltages that high, the current handling ability of the output MOSFETs is going to be massively lower, because as with electronic components, as you increase the current handling, you generally have to decrease the voltage handling and vice versa. So high voltage MOSFETs will generally be lower current, therefore we may need more of them. So if this was the 2 ohm or the 4 ohm version, we would likely see these locations for output MOSFETs populated with a different higher voltage, lower current version of the output MOSFETs. So there's no need of adding any additional 90N20Ds in here. It will just increase the cost of this amplifier unnecessarily, put more strain on the drive circuit for no reason, without any real benefit to the amplifier's operation. So that's just another way that they have designed this board to be interchangeable with the different variants that they offer, without having to redesign a whole new PCB for every single one. So that's fantastic efficiency, cost saving in manufacture here. And you can also see that they've written on the transformers here that these are the 1 ohm version transformers, because the voltage on the secondary will need to be different for each of these different variants of amplifier. So we'll need to change the transformers, caps, FETs, possibly these caps in the output section, and a few other bits, but the rest of the surface mount components and stuff can pretty much stay the same. It also looks like this PCB is shared with not only other 8K variants, but also the 7K and the 10K. So obviously, perhaps in the 10K version, we would see these locations populated with some MOSFETs to take the higher power, a higher current that will be drawn from the output section. So it's an interesting one, because obviously to add the additional components that would be required to change this amplifier from an 8K to a 10K version, you can see there they would just change this for the 10K 1 ohm transformer. The PCB is still the same, so the cost difference to Powerus to go from the 8K to the 10K would be pretty negligible, like perhaps a few dollars more per board. I don't know what the price difference to the customer is between the 8K, the 10K, and the 7K, but I imagine that the steps are considerably more than it would be for the additional cost of the components to go up to the 10K. So it's actually a really good business model in that sense, because Powerus can have hundreds and thousands of these boards printed, but still offer a wide range of amplifiers, and it doesn't really cost them any different, but they can charge more for the 10K version, for example, over the 7K version, without really much difference in their own costs. So from a consumer point of view, as a customer, it doesn't really make a lot of financial sense getting the 7K, because you're essentially buying a 10K anyway, and just with some, lesser components and lower voltages and stuff inside. Yeah, it's an interesting one. I guess it's just the way that they've decided to do their business model. But I have a huge amount of respect for the guys over at Powerus for not masking all of the component values, for making it super easy for technicians, amateur technicians, perhaps even to perform a repair on this. And also, not only that, over here on the PCB, there is printed some contact details for the technical support and to buy original components for these amplifiers directly from Powerus, which is just absolutely fantastic. You know, as an amateur repairer, if you're looking to get into amplifier repair, or maybe even if you're quite a skilled user and you've got one of these and you think you might be able to give a go at repairing it, you can get in contact with them, buy the original parts for the amplifier, and they'll be easily talk you through the different areas on the board with it all being labeled, and you should be able to carry out a successful repair. This is really shaping up to be a fantastic piece of kit. Not only is it built and assembled really well, but I have a huge respect for the way that this amplifier has been designed and the thought that has gone into the serviceability and preventative measures of excessive damage if this amplifier was to fail. But now let's actually power it up and see whether all of these decent things we've seen so far are backed up with a good operation of the circuit itself, and see how happy it is running idle into different loads and the actual operating characteristics of this amplifier. Okay, so firstly, let's start by probing the power supply gate leg, and let's see whether we have a soft start by means of a gradually increasing dead time on the gate drive. Yes, we do. As you can see there, the duty cycle starts off at 0, gradually increases to what would be 50%, and then when it starts to realize that this is a regulated power supply, as you can see here, the duty cycle is now only sitting at 37.2%, and that is because this amplifier, it has a regulated power supply. So we've got 12 volts going in at the moment. As we turn the voltage up beyond 12 volts, so I'm going to turn the voltage up now into 12, 13, etc. You can see there that with the increase in voltage, in order to maintain a fixed rail voltage, the duty cycle is massively reduced all the way down to 6.7%. And if we give it 14 volts, you can see there it's even lower, down at 6%. If I go down back now to 12 volts and go down below 12 volts, we are now at 11 volts. We have almost a 50%, we have a 47% duty cycle there in order to keep the rail voltage up to as high as possible. So the cutoff point for the rail voltage will be with an input voltage of 12 volts when it starts regulating the power supply section and keeping the rail to a fixed point. And we can see that here, if I probe the actual rail itself, we have a 178 volt rail. If I increase the voltage from 12 volts all the way up to 13 and 14, we can see that we only jump up to 184. So 184 is the maximum rail voltage this amplifier is ever going to run on. If I bring it back down, 13, 12. So when I'm down to 12 volts, the rail voltage is still at 183. If I sink down below 12 volts to 10.5 volts, the rail voltage now sinks down to 159. So that power supply regulation is capping the rail voltage at a maximum of 184 volts, which is only about 16 volts below the MOSFET breakdown voltage and the limit on these rail capacitors, which are 200 volts. So yeah, very, very close to the limits. This amplifier is running the components very, very close to their voltage breakdown limits. So the power supply switching frequency is really, really low, down at 20 kilohertz. That's a little disappointing. Obviously, with a higher power supply switching frequency, you'll get more recharges of the rail caps per second, and that's really, really low, much lower than you generally tend to see. With the advancements in transformer design and with the drive circuits and the MOSFETs and stuff, that could really be bumped up to a really, really high power supply switching frequency, which would actually allow the power supply to generate more power, to be able to pass more current onto the output section. So I think that could be perhaps worked on, because it's a little low. I'd have to understand exactly why they chose such a low power supply switching frequency for that. Now let's go over to the output section. Let's see what is the sample frequency or the Class D switching frequency of the output section. Again, super, super low, 88 kilohertz. That is some of the lowest output Class D switching frequency that I have seen, especially considering this amplifier is supposed to be a full range amplifier. Obviously, with the higher the switching frequency, the more samples you get of the sine wave. So generally, in full range Class D amplifiers, we will generally see a switching frequency of anywhere from 350 kilohertz up to 850 kilohertz in car amplifiers amplifiers that I see, much higher in higher end kind of PA and home audio amplifiers, but in a car audio you know, application, generally that will be super high. So with this being down low at 88 kilohertz, this is actually perfect for subwoofer applications. Subwoofer, obviously low frequencies, you don't need as high of a sample or switching frequency, and having a lower switching frequency on the output section actually allows the MOSFETs to run far more relaxed, and there are going to be far less switching losses and cross conduction and stuff, because the MOSFETs are turning on and off way slower, and there's much less you know, tight tolerances between the times when they turn on and turn off for you to have to deal with when you're designing the drive circuit. So this is actually great for a subwoofer amplifier. I wouldn't, however, expect this amplifier to sound very nice at all on higher frequencies, especially in the tweeter range. But I guess with an 8 kilowatt amplifier, that's not what you're going to be doing. You're going to be absolutely blasting this with some PA speakers, not really caring about the SQ, just going for as physically loud as possible. So this lower switching frequency on the output section is great in terms of reliability and efficiency, but not so great in terms of sound quality on the higher frequencies, which personally I wouldn't be caring about in an amplifier like this anyway. What is good to see though is that the drain wave is incredibly good shape, very low ringing on the drain output, and if we probe the gate, let's have a look at what the gate drive looks like as well. We've got very low gate resistors in line, so it should be very clean looking. Yeah, that's fantastically sharp. Got a little bit of a dip on this, is very minor, very minor. That's when the FET is turning on, and when the FET turns on, it draws a little bit of current from the gate drive, obviously, and then whoop, straight up, and then very quickly off. Very quickly off. And that capacitance from the gate when it's turned off is dealt with very quickly through that diode to ground to turn the FET off very fast. Okay, so I've had this running for a little while now, and the output MOSFETs are staying nice and cool, to be honest. Yeah, like I say, on the Korean full bridge amplifiers that are coming out, the output MOSFETs, they run up to like 40-60 degrees within the first minute of operation without being clamped to the heatsink, which is terrible. Yeah, the output MOSFETs are staying absolutely stone cold on the output section, which means that there is absolutely minimal cross conduction, minimal switching losses, and it's idling really happily. The only things that are getting hot in the output section when the amplifier is idling are the two output inductors, which is perfectly normal because they are doing work. They're filtering the high frequency switching waves from getting to the speaker terminals, and the drive circuitry, and most importantly the voltage regulation circuit is getting quite warm, which is what I was saying before. Obviously you've got linear regulators here, which aren't as great as using like buck converters or anything like that. Next thing I want to do is look at the preamp section. I want to see, are the filters labeled accurately? What kind of frequencies are they filtering normally with stuff on minimum and maximum, etc.? How is that exactly working? So I'm going to start by putting 50 Hertz, which should be pretty untouched by all the filters based on their markings here. And we're going to see exactly how the preamp filter is operating. But one thing I thought was worth noting to start with is that, okay, yes, there's a bunch of noise on the speaker terminal on idle anyway, so your subwoofer coil will filter that. That's not a problem, but it might be a bit hissy if you're using tweezers or something. But yes, with 1.9 or almost 2 volts peak to peak of RCA signal going in, with the gain on, or the level, sorry, with the level on minimum, which should be 6 volts, it's actually completely defeat to infinite. So with that on 0, we have no output, and the second we turn it up just a touch, we start getting output. So this is actually completely muted when it's on 0 or 6 volts, and you have to turn it up just a touch to start getting any output through. So don't take too much notice of the 6 volts or 0.25 volts on there. Just go by the clip light. You also notice that as I start to increase this and the sine wave amplitude comes up a little bit, even just a touch, you'll start to hear the fans come to life. So the fans are actively controlled based on the amount of signal. So when the amplifier is idling with no signal, you won't get any fans, which is quite nice, because if you're sitting there without any music playing, it sucks to listen to the fans all day long. And then only when you're playing music do the fans come to life. Okay, so the next thing I want to look at is with the low pass filter down at bare minimum on 80 Hertz, I want to see how much above 80 Hertz is still coming through the amplifier at a reasonable amplitude. So with a 50 Hertz input, we have 13.4 roughly volts RMS. So I'm going to increase this now. 60, still got 13. 70, got 12.4, so a little bit reduced. 80 Hertz, we have still about 12 volts, so we've only lost about a volt there of RMS on the output at 80 Hertz. So with the low pass filter on minimum, you are pretty much, look at that, that's all the way down to, what's that, like 30 Hertz now? So 30 Hertz, we're at about 14 volts, and all the way up to 80 Hertz, we're still at 12.4, 12.2 volts. So yeah, that's pretty way higher than you would generally have on a street-based style system anyway. You don't really be wanting to be sending full amplitude 80 Hertz to, for example, I don't know, Sundown or Scar or something like that subwoofer setup. It's not going to be very efficient. No impedance rise up at that high. It's going to be way outside of box tuning. Not ideal. So let's just see how high we have to go until it starts really attenuating quite steeply. So we're now going up to 100 Hertz. And we have 11 volts there. So still a reasonable amount of output, but it is starting to reduce now. Keep going all the way up to 140 Hertz, 8.9 volts worth of output. And by the time we get up to 200 Hertz, we have 6.7 volts worth of output sine wave. So to be honest, that is not a particularly steep roll-off above 80 Hertz. Yeah, for the majority of kind of street-based applications or musical systems where you're playing between 25, 28 Hertz up to 50, 60, 70 Hertz, this is going to be letting a little bit too many of those higher kick bass sort of frequencies through. It's going to heat up your subwoofer coil more than a Korean amplifier would do with the crossover filter lower and a sharper slope, because at those higher frequencies there's nowhere near as much impedance rise, and yeah, the subwoofer is not moving as much, so it's not cooling the coil as much, and quite a lot of current is going to be ending up in the subwoofer coil during those higher bass notes that wouldn't be there with a Korean style amplifier with a different preamp section. So that is one of the big differences in what causes Brazilian amplifiers to sound different to your old school Korean or Japanese or Chinese amplifiers. It's in the preamp section. So with a minimum low pass filter at 80 Hertz, it's still too high for the majority of systems to run optimally and to sound smooth and to run cool. So run an active low pass filter a bit lower with a sharp roll off either on the DSP or on your head unit, and that will sort this out. Okay, so what about this high pass then, or subsonic filter as some of you may know it? So the minimum is set to 5. So the minimum is set to 5 Hertz, but I want to see whether it is a pretty much linear amount of voltage from 30 Hertz down into 20 Hertz, and see when it starts to roll off, where the slope starts on the bottom end. And then when we turn it up just a little bit, see how much that affects or that impacts the frequencies that we actually want to hear from this amplifier, like 30 Hertz. So we're going to start with a 30 Hertz sine wave, 31 Hertz sine wave going in with the high pass filter on minimum. And I want to see what point does it start rolling off. So we've got 14.2 volts going in, cranking it down, 24 Hertz, nice, still got 14.1, that's looking good so far. No roll off yet, 18 Hertz, 13.7, so it's starting to roll off now. Just under the 20 Hertz mark, we start to roll off 13.8, 13.5, and let's keep going down. 15, 14, 11. Okay, so yeah, that high pass filter knob is definitely working well for, you know, cutting off at 5 Hertz. We've still got 11 volts going in there at 8 Hertz. So once we get down to 6, 5, still got 10 volts with 5 Hertz. So yeah, that's actually working pretty nicely. Now let's go back up to a frequency that we may want to listen to. For example, 28 Hertz. Let's go for 28. Okay, so with 28 Hertz at 13.7 or 14 volts RMS, let's start increasing this high pass knob and see when it starts to affect our 28 Hertz. Oh wow, almost immediately. The second that I touch it, we go from 14 volts down to 12.7. So if you were to turn this knob up to say a quarter, your 28 Hertz would go from being 14 volts all the way down to 12.7. So yeah, it's starting to affect those frequencies that you may want to listen to straight away. So the roll-off is quite shallow on that, so I would avoid using that and stick to an active low subsonic filter if you can. So you may be thinking, oh hey, that's not so much of a problem, it only dropped it by like 1.3 volts or whatever by turning it up to a quarter. But the problem is that the fact that that's affecting those lower frequencies that you might want to hear, and it's not going to be affecting say 40 or 50 Hertz, all that's doing is that's just emphasizing the higher bass notes and making your lower bass notes sound slightly weaker, which is what a lot of people tend to say maybe about Brazilian amplifiers, is that they don't produce the lows quite as well, and you know, it's all very high kick bassy and stuff like that, and they're not as smooth sounding. And so if you have that high pass filter knob turned up even a touch, even just to a quarter from the minimum point, it is going to cause the amplifier to emphasize the higher bass notes more so than the lower stuff, causing it to sound less smooth. Next, I want to know how the limiter is working. There's two ways the limiter could be working. It could be just a clip limiter, whereby when the amplifier detects that the sine wave on the speaker terminals has reached the internal rail voltage limit or surpassed that, it will then bring down the signal level lower to prevent you touching the rails and prevent it from clipping. That's one method. Or it could be listening to voltage drop across these resistors, which are voltage drop. They're like current detection resistors, like shunt resistors. Could be listening to voltage drop across those, and when it detects a high current or overcurrent situation from the amplifier, it then limits the sine wave amplitude to prevent excessive current being passed through the board. That second method, the overcurrent method, is exactly how the Triumph Smart 3 is able to produce the same power from 1 into 2 ohms. It's just using a fixed current limiter that will detect the overcurrent at 1 ohm and reduce the amplitude of the sine wave to prevent excessive current being drawn in 1 ohm operation, but then in 2 ohm operation the excessive current isn't present, so it doesn't limit that whatsoever. Okay, let's see that clip limiter in action. What I'm going to do is I'm going to increase the level until the sine wave touches the rail voltage, so at the point where the amplifier will clip. Okay, so that's clipping. As you can see there, the sine wave starts to touch the rail voltage. That's with the limiter on 0. As you can see, we can clip it quite heavily there. Now let's turn the limiter to maximum and try and do the same thing. Oh wow, I'm seriously increasing the level super hard here, way past that point, and it's keeping it at that clip point. I'm going higher and higher and higher and higher. Wow, that is super impressive. I've got so much signal going in now. This would be absolutely on the limits of hard clip usually. That is pretty incredible. Okay, but how does it deal with transients? I was doing that quite slowly. It's actually bringing it up slowly. You see that slow rise? That wasn't me, that was the limiter backing off there. Now what I'm going to do is I'm going to just quickly spike the input level to a high point and see, and I'm just going to go on off, and I'm going to see how the limiter reacts. Wow, okay, it takes a long time to come back. So you see, even with the limiter on max, I was able to clip the amplifier quite heavily for a brief moment. Then the limiter kicks in and it takes a long time before it comes back to the original point. So I would say that the limiter, this is like simulating like kick drums perhaps. The limiter is a great thing to have turned on, but bear in mind that it will mess up the dynamics of your music slightly, and it will cause it to sound a bit different, and you know, the level to kind of fluctuate around a little bit. So that's really interesting to see how that works. Yeah, all it is, it's just a clip limiter. So it detects when the sine wave is going to touch the rail voltage, and it will then back off on the audio signal going into the amplifier section to prevent it from clipping. It worked brilliantly when I was increasing the level slowly. It was keeping it just on that point of clip, but if I gave it a sharp burst, it took a moment where there was very heavy clipping going on before the limiter would then come into action, reduce the sine wave amplitude, but then obviously it's very slow to then bring back up to full level. So yeah, if you are running this amplifier, definitely set it up correctly. Don't rely on the limiter, because if you're relying on the limiter, then you're gonna still be letting through some pretty clipped kick drum bass things initially when the kick drum first starts, and then it's gonna sound like the volume kind of dissipates as the limiter works, and then, you know, when there's a break in the bass, it will come back up and then it will go boom, come back down again. So it will sound weird if you're relying on the limiter working 100% of the time, but having the limiter there actually set at max all the time and running the amplifier just within its limits and not clipping the amplifier will protect this amplifier from any situations where the volume gets turned up higher than it should have done, the source is changed to something with a much higher signal level, or something happens where loads more signal ends up going into amplifier than you ever intended. And that is a great feature to have, and it's also great that you can turn it off if you are competing in the lanes and you do need to be able to run the amp into some clipping, like 25-30% clip or something like that, which will make you louder in the lanes for a burp. It's great that you can turn it off to give you that extra power with a bit of clipping. When the amplifier is turned on and idling with no signal playing, we have 4.3 amps worth of current draw at 12 volts. For an amplifier this size, that is incredibly good. That is very, very low. Usually a kind of 8K amplifier from a Korean build house or a Chinese build house will typically draw between 8 and 10 amps at idle due to the horrendous number of parallel MOSFETs and switching losses that you have. So that's really, really awesome. Very, very low current draw at idle. If we crank her up to 14 volts, you can see that the idle current draw is actually even less because of the regulated power supply now having a much lower duty cycle. If we go down to, I don't know, let's say 9.5 volts or something like that, we can see there that the current draw is also less because we now have less overall voltage. So the idle current draw will generally be highest at just the point before regulation starts, which is about 12 volts. So we have a 4.3 amps worth of current draw, which is fantastic for an amplifier this size. Most high quality, well-designed amplifiers will have the output side ground, so the ground on the RCA ring and the speaker terminals if it's a half bridge, but not a full bridge. The ground will be floating or separated or isolated in some way from the amplifier's main power ground. And the reason for that is to do with noise control in the system. When you connect up your RCAs, you don't want to be getting alternator noise or any noise from the other electronics in the vehicle system. You want the RCA's ground to be completely separate from the vehicle's main ground. You don't want it to find a pathway through, a low resistance path through to the main vehicle ground. Most of the Brazilian amplifiers that I have tested so far don't care about that, and the output ground is just straight up connected to the main ground, which means that generally if you run a Brazilian amplifier or a Korean amplifier that also has a connected output to main ground with other amplifiers like a 4-channel amplifier that has a floating output ground to main ground, you will get a crap load of alternator noise. And that is because one of your amps has a connected output to main ground and the other amp has a floating output to main ground. That is the most number one cause of alternator whine and noise when you are running your system in your car. So the fact that this one actually has an isolated output ground to main ground is really fantastic to see in this kind of amplifier. Usually these kind of Brazilian full bridge like powerhouse things don't give a crap about that, and all the grounds just are the same, whereas this amplifier actually has a 1 kilo ohm resistance between the output ground and the main ground, which means that the preamp section over here and all the preamp sections of all your other amplifiers and stuff won't go looking for a ground reference from the vehicle's main noisy ground over here. It will go looking for its ground reference from the head unit, which the head unit will generate or supply its own clean floating ground reference itself anyway. So that's what you want. You want a low resistance path to ground to the head unit ground and not to the main vehicle ground, because that causes a bunch of noise issues. So it's really, really great to see Powerus to incorporate a floating RCA preamp output side ground rather than just connecting it straight through the heatsink or something like that. When you're playing your amplifier into a load, current is obviously drawn both from the output section and the power supply section. This next test we're going to do is to see how well balanced is the resistances in the power supply section and the output section, and how well matched is the current draw across all of the output FETs and the power supply FETs. So what we're going to do is we're going to play a tone into the amplifier, into a load, and over time, over about the course of 10 or 15 minutes, we're going to play a tone and see which of the MOSFETs, output or power supply, get hot first, how much they heat up by, and check that there is equal heating across all the output MOSFETs and all the power supply MOSFETs. What that will tell us is that, for example, in the output section, with all of the MOSFETs heating equally, there is an equal resistance and the current is being drawn equally from both sides of the amplifier and all MOSFETs. And we can see whether there is a higher resistance path in the power supply section or the output section. So we can see, if you're running this amplifier very hard, which section is going to cause the amplifier to heat up the most. Is it the output or is it the power supply section? Generally, most Korean amplifiers, I tend to find that the power supply section actually heats up the most, and the output section stays relatively cool straight away. And in the Chinese amplifiers, the really cheap stuff, the output FETs, they all heat up super unevenly, and that's why some of them are so unreliable. We're killing random single MOSFETs in the output section because one of them is working 4 times as hard as any of the others. So I'm interested to see exactly how this amplifier behaves under a load and what the differences in resistances are in different parts of the circuit. So I'm currently playing a tone into the amplifier, 57 Hertz, not too much amplitude. We're only drawing 12.5 amps from the power supply, so nice and light. We haven't got any of the MOSFET clamps on because I want to see which FETs heat up first. So just going to take a look with our thermal imaging camera and monitor over the course of a few minutes what gets hot first. So as we can see here, I think already actually, the power supply FETs are staying dead stone cold, and the output MOSFETs here are starting to heat up. And so the output MOSFETs there they have the higher resistance. So most of the heat from this amplifier is going to be generated by the output section. I also have one of the smaller models. This is the 1600 watt version, because I wanted to see whether it's the same kind of circuit, just scaled down, or whether there's any kind of stuff that's been cut out from the bigger amplifiers. But honestly, this is just a baby version of the 8K that we've been looking at. It's exactly the same circuit architecture, exactly the same power supply, drive method with the same drivers in the power supply, same output section, same PWM generation circuit, same output drivers in fact, same style of transformer, seated down, exactly the same, really freaking solid. It's literally just a baby version of that big monster, and it shares all of the same benefits and fantastic design and build elements as its bigger brother. So for the price that this is a freaking beast. This is a amazing little amplifier. I highly recommend, if you're looking for something for daily use or whatever, then you pick one of these up. This will be absolutely fantastic and really be super loud and powerful and reliable for its size and price. So should your next subwoofer amplifier purchase be a Powerus amplifier? From what I've seen here, these amplifiers provide the best value for money with some of the best build quality and nicest sensible design circuit and best serviceability from an amplifier. Like, this doesn't cost barely anything compared to what they used to cost back in the day, and compared to Korean half-bridge style. Like, stop buying Korean half-bridge style amplifiers or Chinese amplifiers. That circuit is like 20 years old, super inefficient, unreliable, and they've got nothing new to offer in like 20 years. Stop buying that crap and stop overpaying for it as well. Instead of spending like $1,000 on a 5 kilowatt Korean amplifier, instead spend, I don't know, $600 on an 8 kilowatt Brazilian amplifier, and that way you still have the same dynamic power, but you're also able to use it certified as well, because the amplifier just makes more power and is more efficient in the first place. Bear in mind that I'm just doing this video for your own information. Powerus haven't sent me any of these amplifiers. I wasn't asked to do this review. I just noticed that these were on the market now. They've been being sold in the UK for a while now, and I haven't seen any of them in for repair because they've not been blowing, so I didn't have any idea about how great they were until I actually saw one. So I actually got in contact with the UK distributor for these amplifiers, asked him if it was possible for him to send a couple of them over to me to check out so I could do this video and let you guys know what they're all about. I didn't even know whether they're any good before I opened them up, but I'm very impressed with what I see, and I'm sure that you will be too after owning one. So the only thing missing now from this review is a bench test or a dyno test. As just some of you may know who watch my videos regularly, this isn't my normal workshop. I have literally just moved house about a week ago, just got a workbench set up, so all of my high current power supply stuff is all still at the old address. I wanted to get this video out as soon as possible while I still had these here, so I can't bench test. I don't even think I could bench test this 8K anyway. I need so much freaking power. So what I would suggest you do is I'm going to put feelers out there to guys that do have amp dynos and power supplies that can support this size of amplifier to jump on board, get some amp dynos of these online, so that everything that I've said about how great this circuit design is can be backed up by some real world amp dyno tests to make sure that they are definitely making their certified rated power, and see how they form on the dyno. But yeah, I think that's it for now. Not much more I can say about this. Talked about it for long enough. If you've got any questions about either these amplifiers, or if you want any recommendations what you should buy, shoot me a message to my Barevids Facebook page. I'll reply as quickly as I can. Like I said before, there's no benefit whatsoever to me if you buy one of these amplifiers. I just did this off my own back because I felt like the world needed to see what these amplifiers were about and whether they're any good or not. So if you buy one, great. If you don't, great. I don't give a fuck. Just buy what you think works best for your system and pocket, based on all the information you can gather from reputable sources that are actually telling you about the amplifiers themselves. So take it easy guys, hope you've enjoyed, and I'll see you in the next one.